Welcome back, Physics 30. So this is the MP1.4 section of the modern physics. And earlier we looked at special relativity, dealing with inertial reference frames, frames at rest, or frames moving at constant velocity. And I made mention of what if we have accelerating reference frames. So that's where the general theory of relativity comes into play, looking at gravity and the curvature of space. So we'll state Einstein's principle of equivalence, which is really interesting, and explain what is meant by gravity and the so-called curvature of space. So we have seen that the force of gravity plays an important role in the processes that occurs in stars. Gravity, too, is important for the evolution of the universe as a whole. The reasons gravity plays a dominant role in the universe and not one of the other of the four forces in nature is that it's long range and it's always attractive. So if you look at electric force, magnetic force, it tends to be shorter range, and there's positive and negative. There could be attraction and repulsion, but as far as we know, gravity, there is just attraction, and it can act over long distances. The force of gravity, as Newton described in his law of universal gravitation, was modified by Einstein. In his general theory of relativity, Einstein developed a theory of gravity that now forms the basis of cosmological dynamics. So in the special theory that we've been talking about, Einstein concluded that there's no way for an observer to determine whether a given frame of reference is at rest or moving at constant velocity. So we talked about that in MP 1.1. If you're inside a van that has no windows and if you're moving very smooth, you could do any test and those tests would give you the same result as if that van was at rest. Thus, the laws of physics must be the same in different inertial frames. But what about the more general case in which we have an accelerating reference frame, so speeding up or slowing down? Einstein tackled the problem of accelerating reference frames in his general theory of relativity, and in it is also developed a theory of gravity itself. Now, the mathematics is complex, so we're just going to look at a qualitative treatment of it. So we first start with Einstein's principle of equivalence. So what is equivalence? What is equal? That there is no experiment that can be performed distinguishing between a gravitational field and uniform acceleration, as we'll see. So accelerating and the effects of gravity are equal. That sounds interesting. We'll get to that. The observers sensed that they were accelerating. They could not prove that, in fact, they weren't just experiencing a gravitational field in a particular direction. Conversely, we might think we are being pulled by gravity when, in fact, we are undergoing an acceleration. So that's interesting, and we'll look at some examples that show that. So as a thought experiment, consider a person in a freely falling elevator near the Earth's surface. If our observer held out a book and let it go, what would happen? Well, of course, kind of difficult for us to envision this because we've never been out of feeling the effects of gravity. But if we were out floating in space, we wouldn't necessarily, it'd be difficult to see. So gravity would pull it downward towards Earth, but at the same weight and at which the person in the elevator were falling. So if we were in a free fall elevator, it would be like we'd be falling at the same rate. So we could see the book would simply hover there, as we see over here. So if I'm free falling, we're both falling at the same rate. The elevator's falling, I'm falling, the book's falling. So for this moment in time, it would appear that we were just floating there, even though we're technically falling. That'd be the same exact scenario as if no net forces were acting. So if this elevator was placed out in the middle of space, nowhere near a planet, we would experience this just the same as if we were in free fall. And of course, we can experience that if we go up in a plane. So astronauts, for example, or skydivers, we could experience that in a plane that's in free fall. Inside the plane, we would appear to be floating there, similarly to if we were just simply placed out in space and all the net forces were zero. Okay, and it's kind of hard to envision that because in our reality, there's always an FG pulling downwards. Next, what if the elevator is accelerated upwards using rockets? So if it was accelerating upwards, the elevator would want to move up, and of course we would have inertia of rest. We'd want to stay on the ground, so the floor would be pressing up against us. And guess what? That would be simulating gravity. Interesting. So if the elevator was accelerating upwards at an acceleration, the book, as seen from our observer, would fall to the floor with an acceleration of just as if it were falling due to gravity on Earth. And according to the principle of equivalence, here's where this comes into play now, the observer in that elevator, it would be impossible for him or her to determine whether the book fell because the elevator was being accelerated upwards out in space, or because we were in a gravitational field that was pulling things down. So that is interesting. We have no way of distinguishing whether we are experiencing gravity or whether gravity in a particular direction or an acceleration in the opposite direction. So that brings some interesting things here in terms of a light experiment. The principle of equivalence can be used to show that light ought to be deflected by the gravitational force due to a massive object. Consider another thought experiment in which an elevator is in free space where virtually no gravity acts. If I had a light beam, so it starts over here and we're just shining it across the wall, of course it would hit the wall on the opposite side if it was a laser beam. If the light beam is emitted by a flashlight attached to the side of the elevator, the beam travels across the elevator and makes a spot. Makes sense, right? But if instead the elevator was accelerating upwards, such as seen below, the light beam still travels across in a reference frame at rest. In the upwardly accelerating elevator, however, the beam is observed to curve downwards. So instead of going across, it's going downwards. So to a person up there, it appears to be, oh, what's going on? Why is my light beam going down now? So why would that occur? Because during the time the light travels from one side to the other, the elevator is not moving up at constant velocity. If it were, the light beam is undeflected, right? Elevator goes up, I go up, light goes up at a constant velocity, so it hits the side. Again, it'd be like as if the elevator is at rest. But if during that time that light beam was leaving, the elevator sped up in that direction. The light beam is no longer speeding up with the elevator because it's on its own out here. To the light beam, it's going across perfectly, but the elevator moves out of the way and causes it to hit down there. And of course, to a person on the elevator, it looks like it's curving downwards, whereas someone outside the elevator, well, the beam just went straight across. So next we note that according to the principle of equivalence, an upwardly accelerating reference frame is equal to the downward pull of gravity. So if I'm accelerating upwards and the beam goes down, the same would hold true as if there was a big planet here that was underneath my elevator. It would be pulling the beam down as well in a curve. So hence we can picture the curved light path in B as being due to the effect of gravity. Thus, from the principle of equivalence, we expect gravity to exert a force on a beam of light as if it was bent out of a straight line path. So isn't that interesting? The effect of a downward pull is equal to acceleration in the opposite direction. All right, maybe we'll stop there, and then we'll look at part 2 here in a bit.